Okay, now let's look at how this linearization and linear approximation is related in this concept, so-called differentiability. And here, if you notice, the previous discussion over here, we have that, right? And we said the difference between the original function f and its linearization is indeed a linear approximation. Okay, and this difference between f and the linearization could also be treated as the so-called the error of the linearization to this original function. Okay, and we want to see or quantify how does this error is behaving when we look at those x and the y, and way that to make them getting closer and closer to the point A, B, where we write this linearization. So first of all, we need to clarify some concept. So this is the linearization of f of xy at the point A, B. All right. So this is the error of linearization. Okay. So we want to look at this limit. This limit is dividing. We're dividing the error by this quantity. What is this quantity? This quantity is indeed the distance between 2 points. One point is xy and the point AB. So the formal concept of differentiability is that if this limit, which is the error over the distance, is going to be 0, so the ratio between the error and error of the linear approximation or linearization to the distance of the point xy to the center point AB is 0, then we say this function is differentiable at the point AB. So how do we understand it? So let's look at the geometric interpretation. Well, before we jump there, let me remind everybody, how do we write this linearization? Okay, so this is what I have. Well, if you still remember the equation of a tangent and plane, which is z equals linearization, and the geometric description over here is pretty clear if you look at the graph of function and the tangent plane. So this is the tangent plane at point P. Okay, so the logic over here is that if we are starting at a point in the xy plane, this is the xy plane, this is the z, right? And what we should see is that by looking at this point xy in the xy plane, we're shooting up one laser vertically above this xy point. We're going to intersect both the tangent plane and the graph of function. Okay, remember this tangent plane is z equals L of xy, which is the value of the linearization. Value of linearization. And here, at this point of intersection. Okay, we got the function value. V equals f of xy. Okay, and then the distance between those 2 points of intersections will be the difference of the function value and its linearization. And then this difference is supposed to be the linear the difference we had when we talk about the linear approximation, right? And then this is also the error that we're talking about a moment ago. Now, obviously, there's another value we could think about, which is the distance d from this point xy0 in the xy plane to the point AB. So remember here, d is x minus a squared plus y minus b squared. Okay, so do you still remember the limit definition? So what it asks for is that when you are getting closer in the xy plane from any point xy to the point AB, all right, so that distance is in the denominator, and another distance, which is error over here, is the distance from the approximation, which is in the tangent plane, to the actual function value on the graph function. So this ratio is having a fixed. This ratio is having fixed limit, which is 0, which means if you're getting closer, if you're wandering around as a person standing at this XY spot and shooting a laser vertically above your head, and the distance ratios, one distance is the error, the other distance is the distance from point xy to the point AB in the xy plane. So this means when we have this limit of xy approach AB, this distance E over D is 0, means the error between your function value and the linearization is going to become smaller and smaller and approach 0 much faster than the distance between the point xy and the point AB. Okay, so what does this mean? Geometrically, this means the plane will be a very good approximation, or getting really close to this this tangent plane will be getting really close to the graph function. We are getting closer to the point A. This is what we mean by the differentiability. So this means if a function is differentiable, the tangent plane will be a good approximation to the graph function. The linearization will be a really good approximation for the original function. Okay, so now we sort of wrap up the introduction of the linearization and linear approximation in the tangent plane. And we also discuss a little bit of how do we interpret those concepts. Now let's look at another example. We want to find the points on the graph of this where the tangent plane is parallel to this plane. Well, first of all, what is the tangent plane? How do we get to the tangent plane? Well, it has to be z equals L of xy, and then the L of xy is the linearization, which is supposed to be f of AB plus partial x of AB times x minus a partial y of AB times y minus b, right? So for this tangent plane, we did discuss, we can make this equal. The tangent plane is having the normal vector. So what is the normal vector of the tangent plane? So normal vector of the tangent plane is, as we discussed before, this is, and the -1 is the normal vector, right? Well, if you do not like -1 for the third component, you can multiply -1 throughout to the entire vector, make it pointing upwards. But if the third component is negative, the vector is pointing downwards, right? So we want to have something that is pointing upwards. This will be the normal vector. Okay, so for the given function, given z equals x times y cubed plus 8y -1, what is partial f partial x? Well, here partial f partial x is indeed partial z partial x, because f is z. Partial g partial x, I think it is y cubed plus 0, right? So it's y cubed. And how about the partial f partial y? The partial z partial y, and z is xy cubed plus 8 times y to the -1. So this is partial xy cubed partial y plus 8 times partial y to the -1 partial y. This is x times 3 times y squared plus what I think are actually negative. Let's just wait. 8 times -1 y to the power -2. So partial f partial y equals 3xy squared minus 8 times y to the -2. All right. So we know the normal vector of tangent plane at any point is negative partial f partial x at any point. Well, at any point AB, right? But here we don't have the AB. We just use the general variable to indicate the choice could be fairly made. And then partial y is 3xy squared minus 8 over y squared. Okay, and positive 1. So this is the normal vector on any part of the graph function. Well, depending on where you choose this x and y, right? And this vector is what? The original question. Let's look at the original question. The original question is asking us to find the points on the graph of this function where the tangent plane is parallel to this plane. So how do we make two planes parallel to each other? If we know their equation, then if you do, well, even do not know their equations, if two planes are parallel to each other, the two normal vectors will be parallel to each other. So what is the normal vector of this plane? Let me write it here. Normal vector hopefully, we still know how to find it. It is 2, 7, 2, right? Okay, so we know this plane is having fixed normal vector, and we know the tangent plane on the graph function is having this normal vector. Then what we should do? We need to find xy such that it is parallel to this 2, 7, 2. So how do we get it? Well, do you still remember the feature of the two vectors are parallel to each other when we talk about the calculation about the vector? Yep, that's right. Then we need to do this. We need to set the two vectors are parallel to each other means one vector is a scalar multiple of the other. Okay, so we have three equations to set up, which means negative y cubed equals 2 lambda 3xy squared minus y 8y to the negative 2 equals 7 lambda. And then y equals 2 lambda. The last equation is telling us a lot of things, or just one thing maybe. It tells us lambda equals 1/2. If lambda equals 1/2, we put them back in there. So we have two equations for x and y value. Do we know what they are? I think the first one is negative y cubed equals 2 times 1/2, which is the 1. So this means y cubed equals negative 1. So y cubed is what? Well, y cubed equals negative 1. So y cubed equals y equals negative 1. Okay. And then we can plug this y equals negative 1 and the lambda equals 1/2 into the second equation. And we solve 3x times negative 1 squared minus 8 times negative 1 to the power negative 2 equals 7 times 1/2. So we get what? We get 3x minus, well, this is the 1 again. Okay, so this means 3x equals 7/2 plus 8, which is 7/2 plus 16/2, which is 3/2. Is that right? Maybe not so quick. Let me see. I think we are missing something. Oh, here. This is negative. This is negative, right? So I think I have negative here, but I think I forgot to multiply negative 1 to this. This is important. So this is negative. Yeah, this looks better. This negative, negative. Oh, then this is negative 3x, and then subtract 8. That's interesting. This is 7 minus 16, which is negative 9, right? Okay, so now we have negative 3x equals negative 9 over 2. So x equals 3 over 2. So x equals 3 over 2, y equals negative 1. And then we can find the point. So this is the point that we are looking for. All right. So there's one note I want to make, which is over here, I'm using this x and y variable to set the normal vector. You can, but in our previous discussion, we use the a and b. You can change this y to be b, x to be a. That doesn't change anything about the calculation. All right. And then the bottom line here is that you need to find the normal vector of the tangent plane, and to make it a parallel to this given normal vector of this plane where we want our tangent plane to parallel it. Okay, let's just stop.